Let's see a demonstration of performing a Pearson chi-square test of association. In the first demonstration, we created a cross-tabulation table for gender by purchase. This table indicates a possible association between the two variables. Now we want to run a formal test to determine whether the association is significant. Let's look at the code. The proc_freq step requests a cross-tabulation table for gender by purchase, as in the earlier program. But this time, we're working with the Sales Inc. dataset that we created instead of sales. To perform a Pearson chi-square test of association and generate related measures of association, we'll specify options in the tables statement in proc_freq. Remember that you add options at the end of the table statement following a /. The chi-square option produces the Pearson chi-square test of association and the measures of association that are based on the chi-square statistic. The output from this option alone will tell you whether there is a significant association between the specified variables. Let's also add some additional options that are related to measures of association. The expected option prints the expected cell frequencies, which are the cell frequencies that we expect under the null hypothesis of no association. Cell chi-square prints each cell's contribution to the total chi-square statistic. No call suppresses the printing of the column percentages. No percent suppresses the printing of the cell percentages. Finally, we'll add the rel risk or relative risk option to print a table that contains risk ratios, probability ratios, and odds ratios. Let's submit the program. The log shows that it ran without errors. At the top of the output is the requested cross-tabulation table for gender by purchase. The total number of observations appears in the bottom right corner. Notice that we are working with a large sample. You can see how the options in the table statement change the statistics that appear in each cell. The actual frequency appears first. Next, the expected option generates the expected frequency. The expected frequency is the count that we'd expect if the null hypothesis of no association between the two variables is true. The cell chi-square option generates the cell chi-square statistic, which indicates how much that cell contributes to the overall chi-square statistic. The formulas for calculating the cell chi-square statistic and the overall chi-square statistic are shown here. The no column and no percent options suppress the column percentages and row percentages, respectively, which would otherwise appear by default. The row percent indicates the percent of females or males in each purchasing category. We want to identify the customers who spent at least $100, so let's look at the row percentages in that column. Approximately 42% of females and 32% of males spent at least $100. We compare these two values to test for a difference between the percent of males and the percent of females who spend this amount. The next table contains the Pearson chi-square test and Kramer's v-statistic, as well as other tests and measures of association. The chi-square option in the tables statement generates this table. At the top are the overall chi-square statistic and its corresponding p-value. The p-value is less than 0.05, so we reject the null hypothesis. This value tells us that there is an association between gender and purchase. In other words, the observed difference between males and females spending at least $100 is statistically significant. The Kramer's v-statistic measures the strength of the association that the chi-square test detected. This is a two-way table, so the Kramer's v-statistic can range from -1 to 1. Here, the Kramer's v-statistic is close to 0, which indicates a relatively weak association between gender and purchase. The chi-square test might have detected an association because of the large sample size and not because of the strength of the association. Here's a question. What effect does a decrease in sample size have on the chi-square value, the p-value for the chi-square statistic, and Kramer's v statistic? The Kramer's v statistic is not affected by sample size. However, if the sample size decreases, the chi-square value decreases, and the p-value for the chi-square statistic increases. The last table shows estimates of the relative risk for the row 1 variable to the row 2 variable in the cross-tabulation table above. The rel risk option generates this table. Before you look at the values in this table, it's important to understand how proc-freq calculates odds ratios. Let's look at the cross-tabulation table for gender by purchase. To calculate an odds ratio, proc-freq uses the classification in the first column of the cross-tabulation table as the outcome of interest, and the classification in the first row as the numerator of the equation. In this example, remember that the first column is people who spent less than $100. So proc-freq uses this as the outcome of interest when calculating an odds ratio. Proc-freq uses females, the value in the first row, in the numerator of the equation, and males, the value in the second row, in the denominator. In the estimates of the relative risk table, the odds ratio of females to males for spending less than $100 is in the first row. However, remember that we are actually interested in the other outcome, spending $100 or more. So we'll interpret this odds ratio as the odds of the row 2 value, males, compared to the odds of the row 1 value, females, of being in the second column. This interpretation is logically equivalent. Remember that you can use the odds ratio to measure the strength of association for a 2x2 table. The odds ratio of 0.6458 means that the odds of a male spending at least $100 are approximately 65%, or 2/3 that of a female. It's often easier to report odds ratios by converting the decimal value to a percent difference value. The formula for the conversion is shown here. In this example, males have 35.42% lower odds than females of spending $100 or more. An odds ratio of 1 would mean no association. However, the 95% confidence interval does not include 1, which indicates that the odds ratio is significant at the 0.05 significance level. This also means that the true odds ratio is statistically different from 1, so it's another way of testing whether the association between gender and purchase is significant. Here's a question. What effect does a decrease in sample size have on the odds ratio value and the width of the confidence interval? The odds ratio is not affected by sample size, but the width of the confidence interval will increase, given that the relative proportions are held constant.